My name is Saeed Fatullah and I'm a PhD student at the Graz University of Technology. It's my pleasure to present our paper, GIO, Generating Efficient Metrics and Frame Readers for Custom Data Formats by Example. One of the challenges that the data sciences face is working with different types of data formats and representation. However, the current tools and frameworks do not help much with this task, which lead to waste time and poor data quality. In addition to that, data science need to write custom extractor to transfer them into metrics or frames. But this is a painful and unreliable process that lacks good tools and framework. So it seems a state-of-the-art reader is not enough. The question is that, is there an efficient and automatic way to get around? Before going to the details, we are considering the source and some problems of custom data formats. Some applications use custom data formats from systems and machines that are hard to analyze. These formats may have complex or unclear structure, such as flat or nested structure, optional keys, multiple delimiters, multi-line records, and repeating groups of attributes. For example, semiconductor manufacturing, smart grid data management, paper production, and waste recycling are types of these formats. Suppose we have a raw data on the disk and we read all or part of it. Current systems offer a limited set of dedicated reader libraries. For example, CSV, JSON, and XML more commonly used in a state-of-the-art platform. We have to choose the appropriate reader based on the metadata of the data. What if no reader is suitable? To address this problem, we introduced GIO, a system that automatically generates readers. In GIO, we follow in these steps. First, we create a tiny example from the input. Second, we identify the import format and create mapping rules. Finally, we generate efficient reader source code. This code will transfer the source data into the target regular formats. GIO is integrated into Apache SystemDS as follows. We only need to provide SystemDS with examples and source dataset path. GIO is implemented as a part of the IO API. It will identify and generate readers and return the metrics and frames as a regular formats. Formally given a custom text dataset D, we ask the user to provide two examples. First, sample raw input strings from selected rows of the dataset. Second, sample frame or metrics correspond to the sample raw. In the rest of the talk, we will generate readers by using these two examples. In order to better understanding, we have prerequisites of a minor publication dataset as a sample raw. In this dataset, each record started with the number index keyword and spans multiple lines, and all lines headed by a keyboard, and the next following text are the values. We have 4 columns of the dataset as a sample frame. For example, the publication ID and 3 author of the publication selected as a group of the group columns of the sample frames. To give a big overview of our framework, we divided this problem into 2 sub-problems. Step 1, we identify the valid set of the mapping rules. By example, Step 2, we generated our readers that can read any datasets of the same formats. In Step 1, we applied cell value mapping function to the samples. There are 2 types of essential mapping result. First, shape and variance function determine the rows, columns, and the sparsity of the data in the custom data format. We need to find types and parameters of this function from the samples. Second, cell value mapping function encoded how the values are extracted from the data. Here is a snapshot of the cell value mapping function with 2 prefixes and suffixes of our example. Our pattern matching algorithm takes a list of strings and find common subsequences as delimiter candidate by computing their character intersections. So as a result, we can see the pattern and delimiter creation of our last step. The next step is code generation. After identifying the mapping rules from the custom data formats, GIO generates source code for reader data in this formats efficiently. We use the template-based code generation approach for parsing primitives, condition, path expression, and value indexing. In this template has 3 steps. First, get metadata from data with a pre-pass step. Second, infer dimension, estimate sparsity, and allocate a matrix or frame block in memory. Third, parse and insert data into the frame by iterating over the raw datasets. In addition, depends on the mapping rules. We generated code for row index, column index, and value parsing separately and instantiate them in the template. We materialize the Java source code and the compile class files at the end of the code generation part. Here we have an overview of the GIO code template and code generation. The details of our templates are in the paper. In order to better understanding, here we have an example of the cell value extraction with compile nested condition. We use the A-minor publication dataset with 4 projected columns of int64 and string types. The overlap patterns are in the prefix 3 with 3 levels and 4 column patterns at the levels 1 to 3. The generated code with nested condition is for the dense access, skips non-projected attributes without parsing. We use the single node with 32 cores and 128 gigabytes of memory as a benchmark of the system. We implemented our framework in Java 11 and used Python 3.8 and C-Lang++ 10 for the baseline. We tested our framework with data sets of different characteristics and dimensions of the dimension to examine its flexibility. As an end-to-end experiment, we bench GIO's readers' performance on full custom datasets. GIO find the rules and codes for the readers that scale well and are better than others. The overhead is low, but of course can be high in sometimes. It is done offline and can read more or large datasets, and it is robust and good for custom data formats. As a micro benchmark, we tested 25 queries on the data with different levels and types. The main goals of these experiments is to avoiding unnecessary parsing and pre-processing steps. We observed that the single-thread readers' performance much better than other baselines, and GIO has competitive performance in the multi-thread readers. This is because GIO skips unneeded attributes and faster than other systems. As a final experiments, we did different workload with projection, which affected performance a lot. We increased the number of attributes from 1 to all. We found that the first observation is RapidJSON is slow because it's suitable for single-thread readers environments. SystemDS does not use projection, so it has good performance when we are reading entire of the dataset. Python does projection, but it's still slow, as well as very slow for ultra-sparse datasets. At the end, GIO scale linearly and perform well in between state-of-the-art readers. In sum, we built a framework for reading custom text data formats. It automatically finds mapping rules from samples and generate code for datasets. In conclusion, our framework correctly identifies mapping rules it yields competitive performance, and it make data analysis easier and can adjust mapping rules and readers manually. Thank you so much.